Welcome back to the Deep Dive. We are cutting through the noise today on a topic that really screams, the future is now.
Yeah.
The low-altitude economy.
Mm-hmm.
Picture the most densely packed cities on Earth. Shenzhen, Hong Kong, Shanghai. And imagine the sky below, say, 1,000 meters, filled with these quiet, autonomous air taxis and delivery drones. That's the promise, right? The LAE.
It is. It's a fantastic vision. I mean, it offers this perceived escape from the gridlock, the paralyzing traffic you get in a Tier 1 city.
Definitely.
But our job today is really to move past those glossy concept videos and, well, perform a pretty honest, data-driven assessment. Where we actually look at the physics, the economics, the infrastructure needed in these hyperdense places. Does the model really hold up?
Exactly. Our mission today is to take this stack of research, technical reports. They detail everything from vertical airspace capacity, operational disruption because of monsoons, and answer one fundamental question for you, the listener. Is the LAE a genuinely scalable systemic revolution? Will it materially replace a significant chunk of road traffic, like even 1%? Or is it just, well, an expensive, incredibly niche, maybe symbolic market for the highest tier consumers?
Yeah, and the data we've looked at is, well, it's pretty unsentimental. It highlights these stark limits on aerial capacity, especially when you compare the volume needed for mass transit against what the regulations and infrastructure can realistically support.
Okay.
We'll explore those specific calculations, focusing on capacity and that massive cost barrier that just immediately restricts this whole market.
So let's unpack this vision. Starting with the geography seems right. If the LAE is going to transform mobility, it has to be viable somewhere. Okay, where does that operational ceiling actually sit? And why is it so critical for places like Hong Kong and Shenzhen?
Right, so when we talk about the LAE, technically, yeah, it's the airspace below 1,000 meters. That's the region where, traditional planes generally don't operate. So it seems like this potential free zone for new aircraft.
A blank slate, almost.
Almost. But for dense urban operations, that 1,000-meter ceiling, it's functionally irrelevant. The practical cap for routine, high-volume, automated flight in a city like Hong Kong, it's much, much lower, often constrained to around, say, 300 meters above ground level.
Wow, okay, so we're not even talking about the upper two-thirds of that low-altitude zone. We're operating in this really tight band, maybe just 100, 200 meters above the average skyscraper height in the core business districts.
Precisely. That tight operational window, it defines the entire battleground for this economy. But even before we get into the vertical constraints, our sources make a very strong economic case that scaling the LAE outside of China's Tier 1 and maybe Tier 2 cities is, well, the quote was totally pointless.
Totally pointless. That sounds harsh.
It does sound harsh, but it's purely driven by population density and, frankly, financial viability.
Okay, I want to understand that severity. Why is the model so utterly dependent on this hyper-urban density? Can't it serve less dense regions that also have traffic problems or, poor connectivity?
Well, it fails on several fronts in those less dense areas. First, demand. The LAE relies on extremely high usage rates. You need that to amortize the enormous capital investment in the aircraft, the vertiports.
Makes sense.
In rural China, the population density is just too low. You simply don't have enough passengers or enough high-value logistics demand within a tight radius to justify building multi-million-dollar vertiports.
And the infrastructure just isn't there to begin with.
Exactly. In Tier 3 or rural areas, there's a total lack of the necessary landing infrastructure, the distributed charging grid, the specialized maintenance facilities. It's all missing.
Right.
When goods need moving there, they rely on established, low-cost road, rail, or maybe river networks. Drone delivery, which, has high operational costs per kilometer, it instantly becomes impractical because the distances are just too long.
So the ROI just vanishes.
It collapses. The passenger volume isn't there, and the logistical cost structure is completely upside down compared to what they already have.
You'd think maybe manufacturing zones. They often involve time-critical movement of components. Seems like a natural fit. But the sources say they're largely unsuitable too. Why wouldn't air mobility solve logistical snarls in, big industrial park?
Oh, because manufacturing inherently deals with heavy, bulky goods. It needs bulk transport.
Like containers, pallets.
Exactly. We're talking tons of raw materials, parts, finished products, the existing logistics networks, roads, rail, high-capacity ports. They're meticulously optimized. They're incredibly cheap and overwhelmingly efficient for high-volume, low-cost transport over short to moderate distances.
Okay.
Introducing air mobility into that specific segment, it just just adds complexity, regulatory overhead, and incredible cost without solving the actual problem, which is moving heavy stuff in massive quantities. It's redundant. It just doesn't make financial sense when a big truck can move 30 tons for pennies per kilogram.
So the system only works when the cargo is either extremely high value, maybe life critical, or when the time saved is worth an absolutely exorbitant premium. That really filters the potential market down to a tiny selection of places, doesn't it?
It completely dictates the viable ecosystem, the money, the infrastructure commitment, the political will, and critically, the target consumer wealth.
Yeah.
It all converges on a very, very small geographic subset.
Let's break down that tiered viability model the sources use. Detail where the actual investment seems to be concentrated.
Absolutely. The viability is a direct reflection of where density and, well, disposable income intersect.
Okay, starting at the top. Tier 1 cities. We're talking Shenzhen, Hong Kong, Shanghai, Beijing. This is really the only place the LAE exists in the form we're even discussing, right?
Correct. This alignment is critical. You've got the high-income users who can actually tolerate premium pricing.
Yeah.
You have the dense vertical infrastructure that makes ground travel inefficient and, justifies these high-value point-to-point air connections.
And the government push.
And you have centralized government support committed to showing technological leadership. So the use cases here are inherently premium. Rapid airport transfers for executives, maybe luxury mobility between CBDs, critical medical supply delivery, high-value logistics where opportunity cost trumps the actual delivery cost. Passenger eVTOLs only start making any economic sense in this very narrow context.
Okay, then we step down a bit. Tier 2 cities like Chengdu or Hangzhou. What's the model there? Still focused on passengers.
Less so, definitely less so. In Tier 2, the LAE seems to shift away from mass premium commuting. It leans much more heavily toward industrial enhancement.
Oh.
We see things like enterprise logistics, B2B movement of specialized, maybe fragile components, or high-value finished items between industrial parks and warehouses. You might also see limited passenger use, focused perhaps on tourism, or maybe highly subsidized routes, often as a public trial or, a political showpiece. It's more about enhancing the industrial backbone, not really replacing the morning commute for everyone.
And finally, Tier 3 plus and rural areas. We kind of already established they aren't viable for mass mobility.
Yeah, they're essentially non-viable for any sustained commercial LAE model. Any operations you might see are limited to hyper-niche, usually public sector applications, things like detailed agricultural surveying, maybe remote inspection of vast energy infrastructure power lines, pipelines in difficult terrain, or crucial emergency disaster response.
Got it.
But the idea of consumer air taxis or widespread e-commerce drone delivery, it just completely collapses in those areas.
So we confirm our foundational finding right away. This whole economy is geographically pinned down.
It confirms that the low-altitude economy, as a scalable financial system, really only exists within the narrow confines of these Tier 1 and Tier 2 economic powerhouses. The market is, it's urban, premium, and symbolic. It's a technology showcase designed to project global competitiveness rather than a genuine attempt to solve systemic congestion issues for the general population.
Okay, so now we know where it has to operate these core districts of Hong Kong and Shenzhen. But now we face the brutal physical reality of their vertical density. This is where the scale of the operation clashes, maybe violently, with the limited space available.
Oh, the clash is immediate.
Yeah.
And it's non-negotiable. If you look at the core districts in both cities, the average building height, it ranges from 150 to 200 meters, often quite a bit higher.
Yeah.
Given the need for safety margins and that practical urban operational ceiling of maybe 300 meters, we're left with this vertical corridor of only 100 to 150 meters to stack all the air traffic.
That is a vertical squeeze of the highest order.
Yeah.
And the number of safe traffic lanes you can actually stack in there, that's critical to the viability of the whole system. The regulatory standards must determine everything here.
They determine the feasibility of the system itself. I mean, if we were forced to use the ultra-conservative FAA standard, which traditionally requires 300 meters of vertical separation between aircraft for high-speed flight, well, the result is devastating.
How bad?
You can fit exactly one usable lane above the rooftops. One lane. For all traffic moving in both directions along a corridor, that's basically zero capacity for any kind of mass market.
Okay, one lane immediately makes the whole concept non-viable for anything beyond, like, bespoke VIP transfers. But China's pushing hard, right?
Yeah.
Pursuing a much tighter emerging standard, trying to squeeze more utility out of that narrow airspace.
Yes, definitely. In their strategic papers and pilot programs, Chinese regulators are targeting a minimum of 100 meters vertical separation. Now, if they achieve this safely, the capacity theoretically improves quite dramatically.
How much?
You might be able to squeeze in up to 3 stacked lanes, for example, maybe a low lane at 200 meters, a middle one at 250, and the high lane right at 300 meters.
3 lanes sounds significantly better than 1, but achieving that 100-meter separation safely, especially in a dense urban environment that requires incredibly advanced and, frankly, still largely unproven air traffic management, doesn't it? What are the real technical challenges there?
Oh, the challenge is enormous. To maintain a 100-meter separation safely, you can't rely on traditional radar and human air traffic controllers. It's impossible. This requires a fully integrated unmanned traffic management system, UTM, powered by near-perfect real-time telemetry.
Right.
The aircraft have to maintain extremely precise navigation, probably relying on high-accuracy GNSS, plus multiple redundant sensors. Any slight deviation, any unexpected turbulence, any sensor failure, it means instant risk of collision in that tight stack.
And we're talking about flying right next to massive buildings in high wind zones.
Exactly. The practical constraints just chew up that theoretical 3-lane capacity almost immediately. First, you need safety buffers near the sheer walls of 200-meter buildings. That effectively narrows the usable space within each lane.
Okay.
Second, wind shear and rooftop turbulence are extreme. Anyone who's been on a Hong Kong rooftop knows the wind speeds can be dramatically higher and much more erratic than down at street level. These forces, they force aircraft to fly slower or take wider safety margins, which instantly disrupts the traffic flow and kills capacity.
And then you layer on all the regulatory no-fly zones.
Non-negotiable restrictions. You've got regulatory no-fly zones over military sites, major infrastructure, densely populated schools, hospitals. These immediately break up any idea of a continuous air corridor.
Mm-hmm.
And maybe more critically, managing lane crossings or merging paths in a 3-lane stack is technically really challenging. If one aircraft has to slow down or pause, like a kind of red light scenario in the sky, the ripple effect through that stack, with only 100 meters of buffer, it could instantly halt the entire system.
Yeah, you can see why the FAA is conservative.
That 300-meter separation is conservative for a reason. It builds in massive error tolerance. Removing that tolerance demands a level of technological perfection we just don't have yet at scale.
So even with the most advanced standard China might adopt, the system is fundamentally constrained to just a handful of highly specific pre-approved corridors. But none of this flies literally without somewhere to land. You need to stress this immense infrastructure hurdle: vertiport scarcity.
Vertiport scarcity is. It's arguably the single most damaging physical constraint on scalability. In dense cities like these, you can't just clear ground space for an airport. Vertiports have to be integrated onto existing infrastructure, mainly building rooftops or maybe large podiums. But retrofitting these spaces, it's a monumental task.
Why are rooftops so challenging in these cities? They look pretty vast from the ground sometimes.
Structurally, they just aren't designed for the stresses of routine flight operations. The primary issues are structural load and dynamics. Rooftops are often only designed to handle static loads, HVAC units, water tanks, that sort of thing.
Right.
They are absolutely not built to withstand the sustained, powerful rotor downwash force created by these eVTOL during landing and takeoff. That requires massive structural reinforcement, potentially right down to the building's core. Plus, many rooftops have slopes for drainage, they're already cluttered with critical utilities, and you need complex fire suppression systems, emergency access points, all installed from scratch.
So this isn't just a quick construction job. We're talking massive, expensive, multi-year retrofitting of existing, often older buildings.
Exactly. Every single vertiport, every charging station represents a massive capital expenditure. It requires complex zoning changes, environmental assessments, strict adherence to new fire codes designed for aviation fuel, or, more likely, high-capacity lithium batteries.
Yeah, the batteries.
This cost and complexity mean the LAE is inherently limited to a tight network of strategically placed, very scarce landing spots. We are talking dozens of landing zones, maybe, not thousands.
Okay.
The lack of distributed infrastructure means the network is confined to these ultra-high-value point-and-point connections, which just ensures it remains niche.
Okay, let's translate these physical limits into actual dollars and capacity. Let's focus on the core promise: passenger eVTOL mobility. We can use that case study route from our source material. Yuen Long, out in the New Territories, to Central, here in Hong Kong, that's a vital high-demand corridor.
Yeah, that route really captures the essence of the problem. It's currently a traffic nightmare during peak hours. Seems like a perfect use case for a quick air hop.
You'd think so.
But first, let's talk candidly about the cost barrier. Given the necessary infrastructure recovery we just discussed, the launch price for a single passenger, it's projected to be immense.
The sources are placing a realistic launch price for a single eVTOL passenger flight, somewhere between HK $500 and HK $800. That's roughly what, US 64 to US $100?
We really need to pause and deconstruct why this cost is so high, even for a relatively short flight. That HK $500, $800, it covers several colossal financial drivers.
Like what?
First, insurance and regulation. Operating aircraft in these highly dense urban canyons requires premium, specialized insurance policies.
Yeah.
They're orders of magnitude more expensive than ground transport insurance.
Okay.
Second, aircraft amortization. These are sophisticated new aircraft. They've mandated high-frequency maintenance cycles driven by strict regulatory oversight. That's expensive. Third, labor. Pilot wages, and these early eVTOLs will absolutely require pilots, are aviation-level wages, not taxi driver wages. And finally, those vertiport access fees. The limited, expensively built vertiports have to recoup their investment somehow, which means high access fees per landing.
And the optimistic future pricing. Only if everything goes perfectly.
Only an aggressive future scenario involving full autonomy, mass manufacturing scale, maybe extensive government subsidies might see prices drop to the HK $200, $400 range eventually.
Okay, but let's compare that launch cost to existing transport options on that same Yuen Long to Central route.
Yeah, contrast that HK $500, $800 price with ground transport, a private ride via Uber or a similar service. Pretty competitive at HK $66 to HK $96.
Big difference.
Huge. Even a traffic-dependent taxi ride suffering from peak hour delays is typically only HK $320 to HK $390.
So the absolute cheapest anticipated eVTOL flight is still more than double the most expensive ground taxi ride, potentially. This is where I have to push back a bit. If the Hong Kong government is setting up this working group, prioritizing this as we'll discuss later, isn't there an expectation that infrastructure costs will be subsidized or somehow lowered to make the consumer price more competitive?
That's a critical challenge, absolutely. While governments can subsidize the infrastructure build-out, the operational costs, insurance, maintenance, specialized labor, those remain fixed and extremely high.
Right.
And if the government artificially lowers the price too much, it actually risks stifling private investment in the system. Why would companies invest if they can't make money? So the short answer is no. An eVTOL cannot logically cost less than a taxi in this initial phase. The regulatory and maintenance overheads are just so much higher than for a simple ground vehicle.
So the competition cannot be price. It has to be purely based on the time value proposition.
Speed. Precisely. It's a value proposition driven by time savings, maybe the experience, and certainly status. The appeal is cutting a potentially 45 to 60-minute peak hour ground commute down to a predictable 10 to 15-minute aerial hop.
Who pays for that?
They're targeting the absolute top-tier executives, high-net-worth individuals, maybe high-end business tourist people who calculate that saving 45 minutes of their time is easily worth a HK $500 premium.
Okay, let's get to the most critical part of this analysis, capacity. This feels like the bottleneck that really exposes the LAE as a niche concept, not a systemic mobility solution. We need to visualize the sheer scale difference here.
The scale difference is it's staggering. Let's start with the existing system. That Yuen Long to Central corridor, just one of thousands of possible routes in Hong Kong. It's served by an estimated 500 to 1,000 taxi trips per day.
Wow.
And that number is probably conservative. It reflects dynamic, flexible ground transport that goes anywhere.
Okay, now compare that massive ground volume to what the sky can actually handle under these tight vertical constraints. Let's assume the best case. The Chinese standard of 100-meter separation, giving us those 3 theoretical lanes. But maybe focus on just a single lane for calculation clarity. And address my earlier point. Why are we stuck using tiny 2-seater aircraft for capacity calculations? Seems limiting.
We pretty much have to use the 2-seater model for realistic projections right now. The vast majority of operational or near-operational eVTOL designs are severely limited by current battery energy density.
5 Codys again.
Always. The required range and payload for operations in this density, which has to include safety margins, regulatory fuel reserves, maybe anti-icing equipment in bad weather, dictates a maximum of maybe 2 to 4 passengers. And 2 is often the most reliable current configuration to guarantee the necessary battery life for high-frequency operations. Larger aircraft just have prohibitive battery requirements and weight. It drastically cuts into utilization time and payload capacity.
Understood. So using that realistic two-seat model, what is the single-lane maximum throughput per day?
Okay, assuming a single lane, maybe 12 operating hours a day, avoiding mandatory dark hours, and a required 2-minute safety spacing between aircraft for takeoff, landing, and flight separation. The maximum theoretical throughput is around 720 passengers per day.
Theoretical.
Theoretical because, as we discussed, real-world constraints, merging traffic, necessary crossing delays, turbulent slowdowns, that red light scenario, they drop the realistic reliable capacity down to approximately 480 to 600 passengers per day, per lane.
Okay, now you need to deliver the critical insight here. Contrast that 480, 600 passenger capacity against the 501,000 taxi trips on just that one route.
Here is the devastating insight. A single vertical airline operating at peak efficiency in perfect weather can barely match the volume of just one specific premium taxi route between Yuen Long and Central.
Just one route.
And that route represents a tiny, tiny fraction of the total taxi market in Hong Kong, which facilitates over 1 million trips daily across the entire city. The LAE, restricted by vertical limits, tight safety protocols, aircraft size, it simply cannot scale to even 1% of the flexibility or coverage provided by the existing ground transport networks. It's physically impossible.
The system is fundamentally capacity limited by physics, not just technology we haven't perfected yet.
Exactly. This confirms definitively that LAE passenger mobility will remain a niche economy. It's strictly defined by limited, linear routes, high cost, and the continued necessity of using secondary transport ground vehicles just to get to and from the scarce vertiports. It's a premium layer designed for speed and status, absolutely not a mobility replacement for the masses.
Okay, let's shift focus from moving people to moving packages. The other core pillar of the LAE promise is autonomous drone delivery, right? Bringing e-commerce straight to your door. But again, the architectural reality of these ultra-dense Tier 1 Chinese cities seems to fundamentally clash with that whole logistical promise.
Oh, the clash starts right at the last mile. The drone delivery concept, it was mostly incubated in environments with low density, think suburban American yards, maybe Australia.
Right, easy drop-offs.
Exactly. That environment just doesn't exist in Shenzhen or Hong Kong. Nobody has a yard or garden for a safe, automated drop-off. And accessing a typical residential or commercial tower block, it involves navigating multiple barriers, lobby security systems, concierge staff, complex keycard access, lift systems. The drone can't just float down and complete the transaction easily.
So the promise of true doorstep delivery is, well, functionally impossible most of the time without a human intermediary to actually manage the package handover and get through security.
It's functionally impossible for most consumer deliveries, yes. Therefore, we have to challenge the mass consumer hype and really define the genuinely viable drone applications in this harsh environment.
Okay, what are those viable uses then? Where does it actually work?
We see 3 primary successful applications emerging. First, warehouse-to-warehouse logistics, like a B2B mesh network. Moving high-value specialized components, often between adjacent industrial parks where maybe road access is slow but the flight path is short and relatively clear.
Okay.
Second, medical and emergency delivery. This is where the opportunity cost of delay is paramount. Things like organs for transplant, specialized radioisotopes, urgent blood samples, speed is everything.
Mental stuff.
Exactly. And third, industrial inspection and high-resolution mapping. Using drones for this saves immense time and cost compared to traditional manual surveys of bridges, power lines, building facades, etc.
Okay, so those make sense. Highly specialized B2B, critical services. But beyond that, why does the drone model fail so dramatically for just standard e-commerce logistics?
Yeah.
Is it still the cost inefficiency?
It is overwhelmingly a cost issue, and it's a cost issue that just cannot be overcome by the marginal utility of a drone for most things. This is the definitive data showing why ground logistics just wins, hands down, for mass market.
How bad is it?
Drone delivery costs are 3 to 5 times higher than traditional ground delivery, even for small parcels.
Can you give us the currency comparison again just to highlight that gap?
Sure. A single drone delivery for a small parcel is estimated to cost somewhere between US $4.20 and US $12.50. That's roughly HK $33 to HK 98 cents.
Okay.
And this is for a pretty limited payload, maybe 2 to 5 kilograms max. Now, contrast that with the ground courier ecosystem in this region, which, let's face it, has been optimized for decades.
Super efficient.
Incredibly, ground delivery costs are a fraction of the drone cost. Maybe US $0.80 to US $2.30, or HK $6 to HK $18 per parcel.
Wow. That HK $70 difference,
Yeah.
potentially. It's insurmountable for low-margin e-commerce goods.
Yeah.
Why would any customer ever pay a 500% premium for a service that's also less reliable because of weather?
They wouldn't, not unless the item's intrinsic value or the urgency absolutely demands it. And this is why the cost model shifts entirely when we talk about those B2B use cases we mentioned. For example, moving a specialized, high-purity chemical compound that's critical for a manufacturing line. If that line stops for 4 hours while waiting for a ground courier stuck in traffic, the company might lose hundreds of thousands of dollars in production value.
Okay, yeah.
In that specific case, paying HK $100 for a drone delivery to shave 45 minutes off the transit time is absolutely worth the 5x cost premium. The calculation changes.
So the high drone cost is only acceptable when the opportunity cost of delay is catastrophic. For standard low-margin consumer goods, the technology is just fundamentally inefficient compared to existing methods.
Precisely. Ground couriers, usually using nimble two-wheelers or maybe increasingly localized autonomous ground vehicles, they are faster in many real-world scenarios, more cost-effective, definitely more payload flexible, and far, far less weather-sensitive for standard urban logistics.
And they can handle the front door.
And they can handle the human element of navigating security and the lobby handover far more efficiently than any current automated drone system. So, the goods carrier reality. It confirms that drones are a specialized tool for B2B enhancement, maybe emergency services, but absolutely not a systemic replacement for the affordable existing courier ecosystem.
Okay, we've established the geographic limits, the physical limits, the economic limits, but now here's where the reality of actually operating in these cities becomes, well, maybe most hostile: the climatic constraints. This feels like the great unstated risk in any LAE business model, the actual climate of tropical coastal Tier 1 cities like Hong Kong and Shenzhen.
The climate it's not just a variable, it's a relentless operational constraint. It severely limits the number of viable flight days per year. These cities are dominated by monsoon seasons, frequent heavy rainfall, persistent fog, and, periodic high winds and typhoons.
Yeah, T8 signals.
Exactly. All these factors combine to fundamentally disrupt both drone and eVTOL operations, pretty much regardless of how technologically sophisticated the aircraft become.
How exactly does this climate translate into guaranteed operational failure or disruption? Is it just a matter of safety, or does it actively damage the hardware too?
It really impacts every single layer of the operation. Hardware first. While manufacturers are definitely improving weatherproofing, most current commercial drones and eVTOLs still struggle. Heavy rain significantly reduces rotor efficiency. They need more power, which cuts into range,
Right.
and it introduces the risk of electronics failure if any waterproofing is breached. Second, navigation. Heavy rain and low cloud cover cause atmospheric attenuation of radio signals. More critically, rain and fog degrade GPS accuracy, and they really mess with sensor performance. LiDAR and visual cameras suffer from backscatter. It basically blinds the aircraft's obstacle avoidance systems. Precision landing becomes unsafe.
So even if the aircraft could physically fly safely in heavy rain, the sensory equipment needed for autonomous navigation just fails.
Exactly. But the final, and maybe the most decisive failure point, is regulatory. The CAAC, Civil Aviation Administration of China, and the accompanying specialized insurance guidelines. They strictly prohibit flights during thunderstorms, periods of low visibility like below specific cloud-based minimums and high winds, say sustained speeds over 25 knots or so.
And those rules are non-negotiable.
Absolutely non-negotiable safety mandates. If the regulations ground the fleet, the system's reliability just collapses instantly.
Okay, if the system's grounded for, like, a third of the year, no time-sensitive business model can possibly sustain itself. We have some shocking data quantifying this operational disruption for Hong Kong and Shenzhen based on average annual weather patterns, right?
Yeah, the annual figures really demonstrate the severity. Hong Kong and Shenzhen experience somewhere between 130 and 160 days per year, where the weather conditions, a combination of heavy rain, high winds, low visibility, are severe enough to significantly disrupt or completely ground LAE operations under current safety protocols.
130 to 160 days.
Yeah.
It's huge. Over one-third, potentially almost half the year, facing operational uncertainty. Let's drill into the Hong Kong specifics just to ground this reality for the listener.
Okay, Hong Kong specifics. It averages roughly 138 days of measurable rain per year. On top of that, it experiences about 50 to 60 days with thunderstorms, and then you have an average of 6 to 10 days where strong typhoon signals are hoisted, which effectively shuts down the entire city and not just aviation.
Right.
So even accounting for some overlap between those conditions, you are still looking at around 150, maybe 160 days where operational capacity is severely impacted or completely zeroed out.
Just think about the business implications of that. For almost 5 months out of the year, a premium eVTOL service is either severely restricted, subject to mass, last-minute cancellations, or entirely reliant on fallback ground logistics anyway.
That is the critical flaw in the mass market pitch. If you are selling a luxury, time-critical service based on speed and reliability, and that service is rendered unreliable or completely unavailable one-third of the time due to predictable climate conditions, well, no business traveler or critical logistics partner can possibly rely on it for essential scheduling.
It kills the core value proposition.
It absolutely does. This operational fragility ensures that the LAE cannot become a truly systemic component of the city's transport fabric. It must, by definition, remain a supplementary, non-essential service that relies heavily on the ground network, picking up the slack whenever the weather inevitably turns sour.
Okay, let's try to synthesize all these constraints into our final assessment. We've established LAE faces these immense, pretty much fixed limitations, a maximum of maybe 1 to 3 usable vertical lanes above high buildings, really high costs, HK $200 to HK $800 per trip, critically low capacity, barely matching one busy taxi route. It fails for mass goods carriage. And then there's this massive weather disruption, potentially grounding operations up to 160 days a year.
Yeah, the cumulative effect of all those constraints, it really forces us to abandon the narrative of revolution. The LAE is fundamentally not going to solve urban congestion or replace existing transit in these Tier 1 cities in any meaningful way. It will likely forever be constrained by physics and climate.
So if it isn't a mobility replacement, how should we accurately define the LAE's true, maybe unsentimental role in this Hong Kong-Shenzhen ecosystem?
I think we have to define its role through about 4 key lenses. First, it is undoubtedly symbolic. It's a powerful showcase of technological leadership, a kind of smart city branding tool. It's designed to attract related high-tech investment, almost regardless of the immediate logistical utility.
Okay, branding.
Second, it is inherently premium. It's an expensive, high-throughput tool accessible only to the few high-income users who value their time savings at a 3x to 5x price premium over alternatives.
Right.
Third, it is operationally fragile. It's entirely reliant on perfect weather conditions and this tightly managed, scarce, high-cost infrastructure. It breaks easily, operationally speaking.
And finally, it's strategically narrow.
Absolutely. It's really only viable for highly specialized B2B logistics where, as we said, the opportunity cost of delay justifies the massive expense, or for extremely limited luxury commuter corridors where status and speed are pretty much the only deciding factors.
Okay. Despite these tough physical realities, the Hong Kong government is moving forward. They have a strategic framework to stimulate the sector. Let's briefly review the key elements of their policy intent, outlined in the 2024 policy address. This feels like a necessary strategic move to position Hong Kong as a technology hub, even if the immediate logistics are shaky.
Oh, the policy framework is definitely a political necessity at this point. The government is establishing a high-level working group on developing low-altitude economy. It's led by the Deputy Financial Secretary, which shows top-tier political commitment.
What's their goal?
Their stated goal is to formulate cohesive development strategies and, critically, try to harmonize the regulatory environments across the border with the mainland, which is a huge task.
What specific actions are they prioritizing to actually get the sector moving?
They seem focused on 3 core areas. 1, pilot projects, testing real-world applications, things like surveys, building maintenance inspections, maybe rescue operations, and some high-value delivery trials.
Okay.
2, regulatory reform. This is vital. They're actively looking at amending regulations to relax restrictions on beyond line-of-sight operations, BLOS, and potentially increasing maximum payload and drone weight limits. You need that to make any commercial operation feasible.
Makes sense.
And 3, infrastructure planning. Developing a roadmap for the complex installation of public vertiports, charging stations, and, maybe most importantly, creating a fully digitized air route network management system.
That digital air route system raises a major point of, well, Potential political friction that needs discussing, this cross-boundary coordination. Shenzhen operates under the mainland CAC regulatory body, while Hong Kong has its own civil aviation department, the HKCCAD. How does that friction dictate where and when flights can even happen, especially between the cities?
That cross-boundary friction is a colossal barrier. It complicates pretty much every aspect of the LAE vision for the Greater Bay Area. The regulatory philosophies, the air traffic control procedures between the mainland SAC and HKCAT are distinct. They're not automatically aligned.
So what does that mean practically?
It leads to regulatory overlap, potential communication conflicts, differing safety standards, different certification requirements for aircraft and pilots. Cross-boundary flights, which are a key strategic goal for economic integration, require painstaking bilateral agreements on absolutely everything from transponder codes to emergency contingency protocols. Effectively, every single cross-boundary flight is treated like an international operation.
Wow.
This bureaucratic complexity severely limits the viable routes and the potential frequency, further reinforcing the LAE's niche nature, especially for that cross-border dream.
So, while the policy is definitely necessary to stimulate related industries like AI, advanced telecoms, digital mapping, new battery tech, the political friction and the hard physical constraints mean this framework will likely only support a very niche system for the foreseeable future.
That's the major caveat, yes. The policy can be seen as successful in that it leverages the LAE as a sort of new production factor. It stimulates high-tech R&D, attracts talent, looks good globally.
Right.
But until we see massive breakthroughs in truly weather-resilient aircraft, ones that can reliably and safely operate in tropical storms and high winds, and until the cost of building and operating distributed vertiports can be brought down dramatically, that strategic ambition will continually clash with the physical limits of space, climate, and regulation. It ensures it remains an elite supplementary service. #tag outro.
Okay, let's try and consolidate our findings for you, the listener. The low-altitude economy in these major Chinese hubs, it represents a monumental leap in engineering and certainly ambition. But based on the cold, hard data looking at capacity, infrastructure cost, and this massive climate disruption, potentially up to 160 grounded days a year, it is fundamentally not a scalable revolution in urban mobility.
Yeah, we have to conclude that it's really a luxury layer. It's an effective high-speed enhancer for very specialized, maybe life-critical logistics. And perhaps most importantly for policymakers, it's a powerful strategic branding tool for these cities on the global stage. It's niche by design, it's capacity constrained by physics, it's financially exclusive by necessity, and it's operationally fragile because of the climate.
And this leads us to our final provocative thought for you to consider. If this technology, constrained as it is by infrastructure and safety, can only really manage to ferry a few hundred premium passengers a day on the busiest, most expensive routes, barely matching the output of just one single taxi line, does the immense public investment required to build and manage this whole new layer of urban airspace truly justify the public benefit? Or should that extremely limited and constrained urban airspace in the world's densest cities be permanently prioritized solely for essential services, emergency response, medical transport, critical public safety operations?
It forces a really hard conversation about priorities, doesn't it? That tension between the desire for political branding and technological leadership versus genuine practical utility for the vast majority of citizens who will likely never use this service.
Definitely food for thought. We'll leave it there for this deep dive. Thanks for tuning in.